What's up, calculus people? We're here today to talk about some more AP problems, and today we're looking at the problems that involve a chart, which I'm just going to call the chart problems. So let's have a quick look at them over here, and let's get started. This time around, we get ourselves into the Top Gun territory. So if you're unfamiliar with Top Gun is a 1986 American action film inspired by the article Top Guns, published in California Magazine 3 years earlier. So that's 1983. The film stars Tom Cruise, Kelly McGillis, and Val Kilmer, along with Anthony Edwards and Tom Skerritt. Tom Cruise plays Pete Maverick Mitchell, a young naval aviator aboard the USS Enterprise. He and his radio intercept officer, Nick Goose Bradshaw, they got great names, are given a chance to train at the U.S. Naval Flight Weapons School at Naval Air Station Miramar in San Diego, California. So, nice California connection. So, on one sortie, which is, I guess, what they call flights in the Navy, sure. In one sortie, Maverick's speed was charted at the following select values of t. And here we got at t equals 0.5. We got Maverick at 740 miles per hour. You can read through the rest of that. So in the first half hour of one sortie, that's from t equals 0 to t equals 0.5, Maverick's F-14 traveled a total of 120 miles. So that kind of takes care of that time interval. You'll notice that the time interval over here only starts at t equals 0.5. So we don't know what happened before that in that first half hour, but we know in that first half hour, Maverick flew 120 miles. Part A. Use the data in the table to estimate S prime of 0.6. Use correct units and interpret the meaning of S prime in the context of the problem. So we better be talking about Maverick and his sweet F-14. Part B, use a right Riemann sum with 4 subintervals to estimate that integral from 0.5 to 1.5 of S of t. Use correct units to interpret the meaning of the integral in context with the problem. So more context, notice how context heavy this is. And part C, use the answer from part B to estimate the number of miles Maverick's F-14 traveled at the end of 1.5 hours. Okay, sounds good, and let's get started. The first question asks us to estimate S prime of 0.6. So never mind that you know with your physics brain that the derivative of a speed is a velocity, there anyways, is an acceleration. Forget about that right now, because we're just going to estimate, well, in order to estimate a derivative, we're going to need 2 points that are sufficiently close to the point of differentiation, which is kind of what we're doing with the limit definition of the derivative anyways. So you'll notice that there really is no choice here. The 2 closest points to 0.6 sandwich it. So there's 0.5 on the left and there's 0.7 on the right. So we're just going to use those 2 points, find the slope between those 2 points, and then we're going to say that the derivative at any point in between them, like 0.6, has to be close to that slope that we find. So let's see, we've got S of 0.6 is about equal to S of 0.7 minus S of 0.5 divided by 0.7 minus 0.5. Next, you're going to plug in numbers there. There we go. Notice that those numbers are from the chart up here, and they are in order, 0.7 on 0.7, 0.5, kind of on top of 0.5. We're going to do some arithmetic, and we're going to get to the answer here. There we go, 290. I know what you're saying. You're saying, why didn't you put units here? Well, like is always my philosophy, I'd like you to write a sentence at the end here, and that's when the units are really going to come into play. So let's write this. In order for you to get a nice summary here, you got to think about what is the derivative. I know it's burning you. You want to say it's acceleration, but it's not. Well, it is acceleration, but that's not the interpretation we want. What we want to say is that since we have the derivative of s, the speed, what we're saying is s is either increasing or decreasing by about 290 something per something. So at t equals 0.6, Maverick's speed is increasing by about 290 miles per hour per hour. So let's dissect that just a little bit. T equals 0.6, naturally, that's where we're estimating the derivative. But Maverick's speed comes from the fact that we're looking at the change in s. And what is s? Well, s up here tells me that it's in miles per hour, and it is Maverick's speed. Next, we got the word increasing, and we know that the speed is increasing because the number that we got, 290, is a positive value. For negative value, you would say that Maverick's speed would be decreasing. 290 is naturally the number we got, but the units that come associated with 290 is miles per hour. And then we're saying miles per hour because that indicates that the rate is changing. So miles per hour per hour. The rate is changing by miles per hour per hour. Remember, this is not an acceleration interpretation. This is how fast is the velocity increasing. So that brings us to a close for letter A. Let's take a look at the next one. So this is our right Riemann sum problem. Naturally, you could expect Riemann sums to be either a right Riemann sum or a left Riemann sum, maybe even a trapezoidal sum or a midpoint sum. But this one happens to be a right Riemann sum. And the first place that you might go wrong is to get the incorrect intervals. So if I'm reading this right, we want 4 subintervals. Let's just count and make sure we have the correct number of subintervals. Here's the first subinterval, second subinterval, third subinterval, and the last 4th subinterval. So we got 4 subintervals. Those are the correct stretches of t. Next thing you want to do is find out what are the delta t's. What is the change in the independent variable? So this is nicely written for you. You might want to imitate this as you take an AP test. From 0.5 to 0.7, what would be delta t? I think that's 0.2. 0.7 to 1.1, that is 0.4. If I don't do any subtraction wrong, that is. 1.1 minus 1.3, that's 0.2 again, and then a 0.2 finally at the end. Notice how in this problem, the delta t's are not consistent all the way through, and that's just to stop you from throwing it all in your calculator and having your calculator do all the work for you. That's not what we want to do here. We want to show all of the necessary steps. Next, you want to estimate the height of the rectangle by, well, not even estimating the height. You want to get the height of the rectangle by looking at the right side of the interval. So what I'm going to do next is I'm going to highlight where is the right side of the interval for all of these next ones. What's nice about writing out the intervals like we did here is that the right side of the interval is literally the number on the right. And if you mess that up, I don't know what to say to you. So at the right side, that is clearly at 0.7. What is the speed at 0.7? Well, that's 798. So let's write S of 0.7 is equal to 798 AU. And we'll continue down the line. Now that we've got all of those, we're going to write out our sum. First of all, showing the products. Secondly, multiplying out the products. And then lastly, adding all the products together. I'll show you what I mean. First one, let's just write down everything that we intend to multiply. Did a little bit of color coding there for you also. Next, you're going to perform all those multiplications. There we go, 726.8. To interpret the correct units, of course, this is going to be, if we had S in miles per hour and we're integrating with the dt, that means that we're going to lose a per hour and we're just going to be in miles. So this is in 726.8 miles, which I'm writing here just to reinforce it. You wouldn't have to write it there until you're ready to do the interpretation. So the interpretation here isn't that difficult. If we're looking at 726.8 miles, then we're talking about how many miles did Maverick fly. And important, we're going to state a time interval. And there we go. Maverick flew approximately 726.8 miles in the time interval 0.5 less than equal to t less than equal to 1.5. Don't make a big deal about it. You know what it is. If you're integrating speed, you get displacement. So this is how far he flew during those, well, this looks like a 1 hour time period. Letter C, take the answer for part B to estimate the number of miles that Maverick's F-14 traveled at the end of 1.5 hours. So again, don't make a lot of big deal about this, but I am going to start with this from the perspective of the fundamental theorem of calculus. Notice that if you integrate a speed function from A to B, what you get is a change in position, position B minus position A. In particular, we're talking about the change in position from t equals 0.5 to t equals 1.5. So that integral that we just figured out, that we just actually interpreted already, that would be a change in position. So if we take that change in position and we add to that the number of miles that Maverick has already flown up till t equals 0.5, then what we're going to get is how many, an estimate at least, of how many miles Maverick flew from t equals 0 to t equals 1.5. So let's see what we write here. So there we go, 846.8 miles. That's how far our friend Maverick flew in his 1.5 hour flight. Which brings us to the important ideas. Presto. The chart of the derivative of r prime. So the first thing I want to impress upon you is that if you need to estimate r prime at any place where r is the function in the chart, you're just going to take the 2 points closest to where you want to estimate, which we're calling C here, and you're going to use the slope formula. Remember, the derivative is a slope, so using a slope formula to estimate the derivative really shouldn't be that strange to you. The interpretation here is r, whatever r is, the context for r that is increasing or decreasing depending on positivity or negativity at whatever the unit is per time. Okay? The Riemann sum. Firstly, do not omit intervals. It's really easy to do. Highly recommend you make sure you have every interval accounted for. Secondly, when you calculate each product, you please show the sum expression. Everything added together. Show that. They want to see that. The interpretation has to be, or will be, a change in the antiderivative in some interval. That's what we're doing. That's the fundamental theorem of calculus also. Since that is a fundamental theorem of calculus, you're going to most likely be using that integral approximation for some kind of fundamental theorem problem or for some kind of an average problem. There might be more, but those are the two big ones that are the approximation is used for. So that brings us to, and of course you can pause it anytime you want if you want to look at that again. That brings us to our check your understanding. A metal wire, 8 centimeters in length, is heated on one end. The table shows selected values of the temperature T in degrees Celsius of the wire heated from one end, or from the heated end. So right at the heated end, the wire is at 100 degrees. 5 inches away from 5 centimeters away from the heated end, the temperature of the wire is 70 degrees, and at the other end of the wire, 8 centimeters away from where the heat source is being applied, the wire is only 55 degrees. So first of all, estimate T prime. We just did that, right? If you want to estimate T prime, you're going to take the 2 points closest to it and estimate, or just calculate the slope. So where is 7 closest to? Well, 7 is closest to 6 and 7. So we're going to use 6 and 7 and their corresponding T values, 62 and 55. Go ahead and write that up. So T prime of 7 is about equal to T of 8 minus T of 6 over 8 minus 6, which is about equal to negative 3.5. So what is the unit here for X? Well, that is centimeters for the end, from the heated end. So 7 centimeters from the heated end, the wire's temperature is decreasing because it's negative at approximately 3.5 centimeters, 3.5 degrees Celsius per centimeter. Can't ask for anything more than that. Part B, write an integral expression of Tx for the average temperature of the wire. Estimate the average temperature by using a trapezoidal sum with 4 subintervals indicated by the data in the table. Indicate units of measure. The average of anything in calculus is an integral. So if I want to find the average temperature, then I'm going to have to integrate that temperature function. There we go. An average temperature is nothing more than the integral divided by a time interval. So let's estimate that integral now. I noticed that it said to use a trapezoidal approximation. So this is going to be a little bit different than what we did before, but the style is still going to be the same thing. First of all, let's get our intervals of X. Check to make sure I didn't skip anything. You know that you didn't skip anything if you see a repeat in those X coordinates. So let me show you what I mean by those repeats. Here's 1 and there's 1 again. Here's 5 and there's 5 again. Here's 6 and there's 6 again. So every left endpoint has this corresponding right endpoint that's the same. So that tells me that I didn't skip anything. Next thing is going to be delta X. Next would be the height, but we're not really figuring out the height. What we're actually doing is we're taking the average of the height on the left and the right. That's how trapezoids are computed. Now, I don't know, when you guys learned trapezoids, if that's what you did, if you took an average of the top base and the bottom base, or you did it, but did you learn that it was the average? We should change that. We should really look at that. The area of a trapezoid is the height multiplied by the average of the bases. That would have helped us out a lot here. So let's figure out the average of all the bases. Ooh, really running out of room here on this one, especially as I'm trying to type it. Now, I haven't gone into showing all those mathematics of finding the averages. I guess we can do one of them. I mean, it's really not fancy. It's just 100, which was the point on the left, plus 93, which is a point on the right, divide by 2, and you get 96.5. I didn't think it was super necessary to show here, but you might want to show that in your work. The next thing for you to actually put in your work would be the sum. So let's get that sum together. And while we're at it, let's put that 1/8 into the equation so we can get the average temperature all rolled up into one equation. We've written down the sum. That's this 1/8 plus 1 times 96 plus 4 times 81 plus 1 times 66 plus 2 times 58. And then we multiplied and added that all together. That got me 75.6875. It says to indicate units of measure. And what are we averaging? Well, we're averaging the temperature. So the units for the average temperature should just be the temperature. All right. There we go. All right, everyone. That's the end of today's calculus lesson. We'll see you next time when we look at more chart problems.